Hello there. In this video, I want to explore what the output would be of a logarithm if we plugged in a complex number. This came about from an exploration where the logarithm, as we learn in algebra and pre-calculus classes, is defined over the domain of x is greater than 0. At x equals 0, we of course get undefined, and at negative numbers, we get non-real solutions, and we'll look at why. So this came about because I thought, what's the logarithm of a negative number? And if you have a calculator with complex capabilities, you'll see some patterns, okay? I should say that throughout this video, you should have a basic understanding of some things, complex numbers, like how to graph them, what the radius is, what the argument is, okay? You'll also want to know general forms. I'm also going to be doing some things in this video that I'm seen in other videos are mathematically inappropriate, and I put that in air quotes. I honestly don't know. I've never been formally trained in a complex analysis class, so let me know in the comment section if I do something wrong. So the first thing we're going to do is define, and I'm actually going to, now that I think about it, I probably should choose a different variable. Let's keep with b. Let's keep with b. And we'll let z be the complex number x plus yi. Now, complex numbers can also be written in their polar form, r times ei theta, where r is the square root of, almost fell back on old habits, x squared plus y squared, okay? And then theta is the argument of z. Now, there's a whole piecewise function that goes into argument of z. I'm going to go ahead and write it down for you. The argument of a complex number is defined to be the two-dimensional arctangent of our components y and x. Now let's really quickly think that we're going to be using arctan. Arctan is a function that is defined between the interval of negative pi over 2 to pi over 2. But when we think about our complex plane, we have a full 360 degrees to rotate around. So we make adjustments like this along the way. So if x is greater than 0, then we're in quadrant 1 or 4. That's where arctan is defined to be between its regular interval of negative pi over 2 and pi over 2. Anytime we're in quadrant 2 or 3, we have to make adjustments. And let's think why. In quadrant 2, x is less than 0 and y is greater than or equal to 0. Well, that would lead a negative result in the arctan the same way as if we were in quadrant 4. So we add pi as a result. And then we subtract pi if they're both less than 0, because we're in quadrant 3, but a negative over negative would be an input into arctangent of a positive, same way as if we were in quadrant 1. Now, in those two, y is also less than or equal to or greater than or equal to, depending. That would mean we would be on the x-axis. But think about if x is equal to 0, then we get a 0 in the denominator, and we're undefined. So this is where we just use the piecewise definition and say it's pi over 2 if x is equal to 0 and y is greater than 0. That would be above the x-axis on the y-axis, which would mean it is a full 90 degree or pi over 2 rotation. If we go the other way and it's on the y-axis below the x-axis, that means x is equal to 0 and y is less than 0. And then finally, if it's 0 over 0, then we're not on any axis, we're on both axes. We're at the origin, and this is where we'll just say it's undefined. So when we're calculating the complex logarithm, we're saying that z cannot be equal to 0. So let's talk about that formula. I'm going to start afresh on a new page. So log base b of z. And I should tell you the complex logarithm that's taught in complex analysis classes is I believe just using a base of e. Because we can use the change of base formula to turn any logarithm into a natural log, and the complex polar form is in base e, we just assume that the logarithm base e is base e. Again, I have never formally taken a complex analysis class, so if I didn't quite nail that, I apologize. So I started my exploration by saying log base b of z is equal to the natural log of z over the natural log of b. And we'll want to remember the natural log of b is a constant in this case. So we're just going to fixate on the natural log of z. And this would be the complex logarithm, z. Now, if we think about natural log of z, that would be the same as the natural log of r times e I theta, because we defined that on the previous page, okay? And now we have a product of two numbers. E to the I theta is one number, and r is a number, another number. So we're going to use the product rule of logarithms to say this is the natural log of r plus the natural log of e to the I theta. Now, at this point, we may see some cancellations we can do. We can cancel the e and the natural log because they're inverses, and we get the natural log of r plus, and we're left with this exponent, I theta. Now, if we were to actually do these calculations, remember that r is the same as the square root of x squared plus y squared, so it's rectangular components. And then I theta, the theta would just be this behemoth right here. And you'd have to know how to operate this piecewise function. Okay? So our final answer of log base b of z would be natural log, pardon me. The natural log of r plus I theta all over our constant natural log of b, and we're done. If you spotted any mistakes, this is not something I'm used to, but I did want in a video establishing how to calculate complex logarithms. Thanks for watching.